This video guides you through the design process of a shallow footing in clay soils, using GeoMechanica Desktop, starting from the initial soil report to defining the final dimensions. Our design path follows 6 key steps, from reviewing the soil report and extracting parameters, to checking bearing capacity, performing a clay shear check, evaluating settlement, and finally selecting the geometry. To define the problem and acceptance criteria, we establish a vertical column load of 500 kilonewtons, a required factor of safety of 3.0, and an allowable settlement of 25 millimeters, all at an embedment depth of 2 meters. Here is the interpreted soil profile from the report, detailing the layers, SPT blow counts, friction angles, undrained strength, and modulus of elasticity across the depth. Critical observations include the water table at 2.3 meters and a 4-meter thick clay layer. The footing is set at a depth of 2 meters to remain above this compressible layer. We test several footing widths because the final dimension is not known initially. Design parameters are typically determined up to a depth of 1.5 times the footing width. This is the setup for our bearing capacity module, incorporating the foundation dimensions, soil properties, and load parameters to begin the initial stability analysis. The results show how allowable bearing capacity varies with different footing lengths and widths. As expected, increasing the plan area generally improves the bearing capacity. Reviewing the safety trends, a 1 meter by 1 meter footing provides a factor of safety of 3.76, which satisfies our requirement. We will proceed with this selection while continuing to check other performance criteria. While the ultimate limit state is satisfied, the design is not yet complete. We must also verify the short-term undrained behavior of the clay and ensure long-term settlement remains within limits. An undrained clay check is essential for saturated layers under short-term loading. Comparing the shear demand of 36 kilopascals against the available 60 kilopascals gives a ratio of 1.67, confirming the design is acceptable. The shear demand value was calculated using the effective and added stresses module, which models the stress distribution through the soil profile. This slide displays the maximum shear check results within the clay layer, visualizing the added vertical and horizontal stresses generated by the foundation load. Finally, we perform the settlement check. We model long-term settlement using drained moduli over an influence depth of 5 times the footing width to ensure we remain under the 25 millimeter limit. Using the elastic half-space module, the calculated settlements are 8.4 millimeters or 7.6 millimeters, depending on the rigid layer depth. Both values confirm our design is well within the 25 millimeter serviceability criterion. The elastic settlement results vary slightly based on the assumed rigid layer depth. With a very large depth, we calculate 8.4 millimeters, and at 5B, 7.6 millimeters, both being well under the 25 millimeter limit. To verify the reasonableness of these results, we examine the Gibson soil behavior. In this model, the soil modulus increases linearly with depth, which often provides a more nuanced estimate than assuming a uniform average. By applying the Gibson model parameters to the foundation geometry and soil properties, we can perform a sensitivity check to ensure our settlement predictions remain robust. Comparing these results shows the Gibson soil approach yields a settlement of 12 millimeters. This is more conservative than our previous estimates, but still under half of the allowable 25 millimeter limit, confirming the design remains valid. The GeoMechanica Desktop modules used in this workflow include tools for capacity, stress analysis, elastic and Gibson soil settlement, as well as graphing and property management. In conclusion, a 1 meter square footing at 2 meters embedment meets all requirements. The Gibson soil calculation, while providing our highest settlement estimate at 12 millimeters, confirms the design is safe for serviceability.